when we look at the different particles, if we want to make a classifications of particles, we're going to say, okay, let's see if we can make a table with everything that I'm. So all particles are either fermions or bosons. So bosons are the exchange particles, and fermions are what we call matter. So this is what we call forces. So these are what Max Planck say, these two, matter and forces, they cannot be separated, right? Now, within the fermions, there are hard particles that we call hadrons, and light particles, I'm going to use another color, that we call leptons. So what are the leptons? Okay, the leptons are the electron, the muon, the tau, and their corresponding neutrinos. Electron neutrino, muon neutrino, and tau neutrino. These are the 6 leptons. Small. Leptons comes from the word light. Small. And the hadrons, we have seen baryons made of 3 quarks, and mesons made of a quark and an antiquark, right? So these are the particles, right? Hadrons are different quark states, leptons are electrons, and all those tiny particles. And then if we look at the bosons, we have 2 types of bosons. The ones that we call gauche bosons, and there we have, like we saw, the photon, the gluon, and the W plus, W minus, and zeta bosons. The photons are responsible for all the interactions between charged particles, like light interacting with matter. The gluon is responsible for strong nuclear forces. This is the exchange particle that makes possible for the protons to stick together and overcome the Coulomb repulsion. And these are responsible for radioactive decay. So these particles are also a very, very short range. So in summary, we have particles like quarks, particles like leptons, and exchange forces. So we have the gluon. So how do these interact, right? So we have the gluon as a boson with a G there. We have the photon, yeah. And then we have the, we have the W plus, W minus, and zeta boson. And then we have a particle that I'm going to put in another color here, which is known as the Higgs boson. So how do these particles interact? Okay, so we said that leptons, we have the neutrino, electron neutrino, muon neutrino, and tau neutrino. And we have the electron, the muon, and the tau as particles, right? The quarks, we have up, down, let me change this. Up, down, We have charm, strange, top and bottom, right? So the gluon interacts with quarks because it's the force that is inside the nucleus of the atom. The photons interact with everything. The Higgs boson, well, the weak forces, they interact between leptons. They interact with also the quarks in the nucleus. And then we have these bosons, the Higgs boson, that interacts with everything. Even particles that have no matter, if they interact with the Higgs field, they bring up matter. So this is what we need to understand now. What is the Higgs boson? What is that field, scalar field? We're going to put it here. It's a scalar boson, not a Gauss boson, scalar, that was predicted by Higgs 50 years ago and actually measured in the Large Hadron Collision, right? So the Higgs boson was a very important particle in the model that interacts with everything in nature. Anything that becomes mass is because of this Higgs boson, which in the slides that I shared with you. So this is a very good song. I encourage you to watch it. This is the lyrics of the song. The universe is made of 12 particles of matter, 4 forces of nature. Wonderful and significant story. It's really fun song. Only 3 minutes. If you learn this song, you learn the words. You know, the problem with particle physics is learning and remembering these words. But coming back to the Higgs boson, this is a video that I share with you in the slides. It's an analogy. This field is everywhere. It is interacting with anything that I said obtains mass, like a photon, right? If a photon doesn't get mass, but a particle that is massless like a photon, if it interacts with the Higgs field, it becomes a massive particle, a particle with mass. So this was proposed by Higgs, and there was a challenge to find out the best analogy, because these things can only be explained by analogies. So in this video, we have the best analogy. I encourage you to watch it, but basically, it says that if someone like Higgs comes into a room full of scientists, because it is Higgs, this man is very popular, it would bring the people closer to him, and that is the analogy, you know. When Higgs walks through a room, people will crowd around him, and that is the effect of how matter appears as mass. It's an interesting analogy, but still, I don't think it fully clarifies what is a scalar field, you know. A scalar field, they're saying that temperature is a scalar field. That is an interesting idea. So, what is a scalar field? What is a Higgs field? Again, we're using models to explain mysteries, but the interesting thing about the standard model is that it is the most successful model, the standard theory, the most successful theory so far to, I don't know, 6, 7 significant figures of accuracy. So this model finally, 12 particles of matter, quarks and the leptons, 4 forces of nature. This is the probably periodic table of the periodic table. This is what explains the periodic table. So what we have learned in chemistry comes from the standard model of physics. All right, so that is An introduction. I like this table, the different bosons or exchange particles. Gravitron is the only one that hasn't yet been, it has been predicted but not measured because it's a very weak force, very difficult to measure. So we haven't yet had the evidence for the particle that is responsible for the gravitational force, but we know that the range is infinite, yeah, and it acts on anything that has mass or energy, right? So this needs to be detected, but this is something that is known. The photons, responsible for electromagnetic forces, infinite range, and it acts on charges. The gluons, responsible for strong nuclear forces. The range is the size of a proton, the size inside the nucleus, right? Probably the size of the nucleus of an atom, and it acts between quarks. And then the W minus, W plus, and zeta bosons, responsible for the weak forces that we see manifesting in radioactivity. So the range is even smaller. And these acts between quarks and leptons, yeah, decay. And then God's particle, omnipresent particle in the universe, a scalar field, whatever that means, yeah. It has an infinite range that goes to the plus and the minus, that goes to the biggest and the smallest. That is the idea of, well, that is probably the reason why it was called the God's particle. And it acts on anything that has mass. So this map or table summarizes the nature, the range, and where it acts on of the fundamental forces of nature. And finally, I leave you there with Brian Greene and a very short introduction to the string theory, which is probably the theory of everything that supports the standard model, but goes beyond that to explain that asymmetry that made the universe possible. That is the big question. And the string theory is trying to explain, okay, how did it start? What imbalance created the fundamental particles in nature? So then at this point, my advice is to pause and play some Quizlets. Before we do any problem, I would encourage you to just, in groups or by yourself, learn the language. So best way to learn the language is click on these two Quizlets and practice a little bit of particle physics. So this is half of the lesson on 7.3. We continue in the next video.